You've probably heard that mitochondria are the powerhouses of the cell, but what you probably haven't been told is that your skin cells don't just need mitochondria to make energy. What if some of the changes you see in your skin when you look in the mirror aren't happening simply because you're getting older? What if underneath those wrinkles, the uneven pigmentation, the slower healing, and the gradual loss of firmness, something much smaller had a significant role? Your mitochondria. Our skin cells need healthy mitochondria to repair themselves, respond to stress, maintain the skin barrier, support collagen production, control inflammation, and even decide what to do when a cell becomes damaged. And as you age, this system can become less efficient. The really interesting question is whether that process is completely irreversible, because researchers are now discovering that mitochondria in aging skin don't simply become old and useless. They can accumulate damage, lose efficiency, produce more oxidative stress, become worse at removing their damaged components, and alter the signals that tell skin cells how to behave. And that raises a fascinating possibility. What if one of the ways to slow down some aspects of skin aging isn't just to put something on top of your skin, but to change what is happening inside the cells themselves? Today, I'm going to show you 5 things that can push the mitochondria in your skin toward dysfunction, how that can contribute to visible aging, and what you can realistically do to protect or improve this system. And the last one is particularly interesting because it involves something you probably already use every day. Let's start with what mitochondria actually have to do with your skin. You probably learned that mitochondria take nutrients and oxygen and turn them into ATP, which is essentially the energy currency your cells use. Think of ATP like money. Your skin cells need it to pay for almost everything they do. A fibroblast needs energy to manufacture and maintain the components of your extracellular matrix. A keratinocyte needs energy to divide, differentiate, and maintain the skin barrier. A cell responding to damage needs energy to repair itself. And when your skin is healing after an injury, almost every step of that process has an energy cost. So imagine that your skin is a huge city. Your collagen-producing fibroblasts are construction workers. Your keratinocytes are the people maintaining the buildings and roads. Your immune cells are the emergency services. And your mitochondria are the power plants keeping the entire city running. Now, here's the part that matters. The problem with aging isn't necessarily that your power plants suddenly shut down one day. It's more subtle than that. Over years and decades, they can accumulate damage. The machinery becomes less efficient. Some damaged mitochondria aren't removed as efficiently as they should be. The balance between energy production and oxidative stress can change, and the signals controlling mitochondrial repair and replacement can become less effective. A recent review in Advanced Dermatology and Allergology described mitochondrial dysfunction as an increasingly important hub connecting oxidative stress, mitochondrial DNA instability, inflammation, cellular senescence, and structural changes associated with skin aging. Another recent review described mitochondria as central regulators of skin health because they influence fibroblasts, keratinocytes, melanocytes, and wound repair. But how do you know if any of this is happening to your skin? Well, there's no simple blood test that you can take at your doctor's office and get a result saying your facial mitochondria are 37% dysfunctional. And that's important because we should not pretend that wrinkles are a mitochondrial diagnostic test. But there are changes we can observe. Maybe your skin doesn't recover from irritation as quickly as it used to. Maybe small injuries seem to take longer to heal. Maybe your skin has become thinner or less resilient. Maybe pigmentation changes linger longer after inflammation. Maybe the texture gradually becomes rougher and less elastic. None of these things prove that your mitochondria are dysfunctional. But here's where the story becomes interesting. If mitochondria are part of the machinery maintaining healthy skin, then the things that repeatedly damage that machinery may eventually become visible on the outside. And the first one is something your skin has been fighting for your entire life: ultraviolet radiation. Think about your skin like a house that sits outside in the weather every single day. Rain hits it, wind hits it, heat hits it, and sunlight hits it. You wouldn't expect the exterior of that house to look exactly the same after 60 years as it did on day one. Your skin is doing something remarkably similar. UV radiation creates oxidative stress and molecular damage, including damage involving mitochondrial DNA. And this is one reason photoaging is so different from simply adding another year to your age. Chronological aging tells you how long you've been alive. Photoaging tells you how much environmental stress your skin has accumulated. Research has found that mitochondrial damage accumulates in aging skin and can also be increased by environmental exposures such as solar radiation and pollution. Mitochondrial dysfunction and oxidative stress have been linked with several visible features of skin aging, including wrinkles, pigmentation changes, and impaired wound healing. And this creates a very important distinction. You cannot stop chronological aging, but you can reduce some of the unnecessary biological damage that accelerates it. That's why sunscreen isn't merely about avoiding a sunburn. You're protecting the machinery inside the cells. But UV exposure isn't the only problem, because once mitochondrial machinery becomes damaged, the next question is, what happens to the damaged mitochondria? And this brings us to the second problem. Your mitochondria aren't supposed to live forever. They are constantly being monitored, repaired, divided, fused together, and when necessary, destroyed and recycled. Think about an airline. You don't keep every airplane in the fleet forever. Some planes are maintained, some are repaired, some are taken apart for parts, and occasionally an airplane becomes so damaged that keeping it in service is actually more dangerous than replacing it. Your cells have a similar system. One of the most important processes is called mitophagy. Mito means mitochondria. Phagy means eating or consuming. So mitophagy is essentially the cellular process of identifying mitochondria that have become sufficiently damaged and sending them toward degradation and recycling. It's the cellular cleanup crew. And here's the fascinating part. Researchers increasingly believe that mitochondrial quality control, including mitophagy, mitochondrial biogenesis, and the constant balancing of mitochondrial fusion and fission, is important for maintaining healthy skin as we age. Now imagine what happens if your city keeps generating broken machinery, but the garbage trucks become slower and less efficient. The broken equipment starts piling up. The city still functions, but not as efficiently. And that's one of the reasons scientists aren't just asking, how can we make mitochondria produce more energy? They're also asking, how can we make the cell better at getting rid of the mitochondria that shouldn't be there anymore? This distinction is incredibly important because sometimes the answer isn't to make the damaged machine work harder, it's to remove it and then build a better one. Which brings us to the third problem. Your mitochondria can become a source of something called reactive oxygen species. Now, before we make this sound like mitochondria are producing poison all day, there's an important nuance. Reactive oxygen species aren't automatically bad. Your cells actually use them for signaling. The problem is balance. Imagine a fireplace. A controlled flame is useful. It gives you heat, but throw gasoline onto it, and suddenly the same fire becomes destructive. Mitochondrial reactive oxygen species can work in a similar way. At controlled levels, they participate in normal cellular signaling, but when oxidative stress becomes excessive, molecules inside the cell can be damaged, and one of the consequences can be damage to mitochondrial components themselves. Now connect that back to skin. Your fibroblasts are trying to maintain the extracellular matrix, your cells are trying to repair damage, your mitochondria are supposed to provide the energy and coordinate the response. But if the machinery producing the energy is itself under chronic oxidative stress, the entire system can become less efficient. It's like asking a construction company to rebuild a damaged building while its own generators keep malfunctioning. Eventually, the repair crew starts falling behind, and that leads us to one of the most important cells in the entire story, the fibroblast. If you've ever heard someone say that aging skin has less collagen, you might imagine collagen as something sitting inside your skin like a layer of filling. But collagen is continuously being made, organized, broken down, and replaced. Your fibroblasts are part of the workforce responsible for this process, and mitochondria are deeply involved in the energy and signaling environment that allows fibroblasts to function. This is one reason mitochondrial dysfunction can have consequences far beyond ATP. It can affect the behavior of the cells that maintain the structure of your skin. And if the construction crew becomes less efficient, the building doesn't necessarily collapse. It just slowly loses its original architecture. The walls become less supportive, the surface becomes less smooth, the structure becomes less resilient, and eventually you notice it in the mirror. But then something even more interesting happens. Some aging cells don't simply die, they become senescent. And this is the fourth problem. Think about a worker who has stopped doing their normal job but hasn't left the factory. They're still there, they're still consuming resources. And worse, they're sending messages to the other workers telling them that something is wrong. That is a simplified way of thinking about cellular senescence. A senescent cell is not simply a dead cell. It remains metabolically active but has undergone a stable change in its behavior, and some senescent cells release a collection of inflammatory and signaling molecules known as the senescence-associated secretory phenotype, or SASP. This is one reason cellular senescence has become such an important area of aging research, and mitochondria are closely connected to this process. Mitochondrial dysfunction, oxidative stress, and cellular senescence can reinforce one another. A damaged mitochondrial environment can contribute to stress signaling. Stress signaling can contribute to cellular dysfunction, and dysfunctional cells can release signals that alter their surrounding environment. So now we have a much more complicated picture of aging skin. It isn't simply you're older, therefore you have wrinkle. It can be more like a chain reaction, and eventually some of those microscopic changes become macroscopic. And this is exactly why the mitochondria story becomes so interesting, because if the system can deteriorate, perhaps parts of the system can also be influenced. And that brings us to the fifth problem. Your skin needs a reason to adapt. This may sound strange because we usually think of aging as something that simply happens to us, but your cells are constantly responding to their environment. Give a cell a particular demand and it adapts. Give it a different signal and it adapts differently. This is called cellular plasticity, and mitochondria are particularly responsive to demand. Your cells can alter mitochondrial number, structure, metabolism, and quality control pathways depending on what they're being asked to do. Think of a restaurant. If you suddenly go from serving 30 customers a night to serving 300, the restaurant doesn't simply tell the existing kitchen staff to work harder forever. Eventually, it changes. More equipment is brought in, more staff are hired, processes are reorganized, capacity increases. Your mitochondria have their own version of this adaptation. It's called mitochondrial biogenesis, the process by which cells increase their mitochondrial capacity. And this is where the story becomes hopeful, because mitochondrial biology isn't completely fixed. Your cells are continuously responding to signals. The question is whether we can give them the right signals. One of the most obvious signals is exercise, because exercise creates an increased demand for energy in muscle. But here's the important distinction for this video. We shouldn't tell people that doing squats will somehow send mitochondria into their face and erase their wrinkles. That's not how it works. The lesson is broader. Your entire body's metabolic environment influences cellular signaling, and maintaining metabolic health, physical activity, sleep, and recovery supports the systems that maintain mitochondrial function. But when it comes specifically to skin, there's another intervention that gets much more interesting: light. Not sunlight. Very specific wavelengths of red and near-infrared light. This is called photobiomodulation. And here's the part that sounds almost too strange to be true. Researchers have been studying whether certain wavelengths of light can interact with cellular components involved in mitochondrial energy production and signaling. One proposed mechanism involves cytochrome C oxidase, a component of the mitochondrial electron transport chain. In laboratory and clinical research, photobiomodulation has been investigated for effects involving ATP production, oxidative signaling, inflammation, wound healing, and tissue repair. And recent reviews specifically discuss mitochondrial dynamics and skin injury in the context of photobiomodulation. But let's slow down down here. This does not mean every red light mask sitting on the internet is a mitochondrial rejuvenation machine. The parameters matter, wavelength matters, dose matters, and there is still disagreement about the optimal protocols for different conditions. So this is a perfect example of where biology can be fascinating without becoming hype. We have a plausible mechanism. We have laboratory evidence. We have clinical research into skin rejuvenation and wound healing. But that is not the same thing as proving that a home device can reverse decades of facial aging. And there's another cellular system researchers are paying attention to, NAD+. You've probably heard this term if you've wandered into the longevity world. NAD+ is involved in cellular metabolism and energy-related reactions, and its availability changes with aging. It also interacts with enzymes involved in cellular stress responses and mitochondrial regulation. So naturally, scientists have asked if NAD+ availability declines with age, could restoring it improve some aspects of aging biology? That's a fascinating question, and the research is moving quickly. But this is another place where the internet has moved much faster than the evidence. A 2026 systematic review examining 113 human and animal studies found that NAD-boosting interventions such as nicotinamide riboside and nicotinamide mononucleotide can increase NAD-related metabolites in humans, but effects on meaningful health outcomes have been inconsistent and often limited to specific endpoints. The authors concluded that clinical effectiveness for anti-aging remains inconclusive. So if someone tells you, take an NAD supplement and your face will become younger, that's much more confident than the science currently allows. But the underlying biology is absolutely worth watching, because we're beginning to understand aging less as one giant switch and more as a network of interacting systems. In fact, a 2026 review described NAD+ as a metabolic hub connecting several biological hallmarks of aging, including mitochondrial and cellular processes. Now, I know what you're probably thinking. If mitochondria are so important, can we simply give them something that fixes them? There are compounds being investigated for exactly this reason. Mitochondrial-targeted antioxidants, agents that influence mitophagy, compounds that affect mitochondrial biogenesis, photobiomodulation, NAD-related interventions, and even experimental therapies designed to interact more directly with mitochondrial membranes. But these are not interchangeable. Some have human data, some have mainly laboratory or animal data, some have evidence for muscle or metabolic health, but not facial aging, and some are still experimental. This distinction matters because one of the easiest mistakes in longevity science is taking a beautiful mechanism and assuming that because something works in a cell, it must work on a human face. It doesn't. Biology is not that simple, but there is something you can do right now that doesn't require a futuristic mitochondrial supplement. You can reduce the things that repeatedly damage the system. And this is where I want to bring the entire story together. If UV radiation is repeatedly damaging your skin's cellular machinery, protect it. If your smoking stopping is enormously more important than adding another anti-aging serum. If you're chronically sleep deprived, don't expect a supplement to compensate perfectly for that. If your diet, physical activity, or metabolic health are poor, those are worth addressing because your skin doesn't exist independently from the rest of your body. And if you're using evidence-based topical treatments, such as retinoids, don't think of them as competing with mitochondrial biology. Think of them as one part of a much larger strategy for modifying the biology of aging skin. And there is one more important point. You don't need to obsess over your mitochondria. You don't need to buy 10 supplements. You don't need to measure every biomarker. And you definitely don't need to believe every longevity influencer who tells you that your mitochondria are broken. There is currently no routine clinical test that can look at your facial skin and give you a simple mitochondrial age that tells you exactly how old your skin cells are biologically. And that's actually a useful reality check. So how would you know if you're doing something beneficial? look at the outcomes that actually matter. Is your skin tolerating treatment better? Is it recovering more efficiently? Is its texture improving? Are pigmentation and inflammation becoming easier to control? Are you protecting yourself from the environmental exposures that accelerate aging? And over the long term, are you preserving the structure and function of your skin rather than constantly trying to repair damage after it has already happened? Because maybe the most important lesson from mitochondrial research isn't that we have discovered a magic way to turn a 60-year-old cell into a 20-year-old cell. We haven't. The more interesting discovery is that aging isn't simply the passage of time. Your cells are constantly receiving signals from their environment. Some of those signals tell them repair, some tell them adapt, some tell them build, and others tell them you're under attack. Your mitochondria are sitting right in the middle of that conversation. They sense metabolic stress. They respond to environmental damage. They participate in redox signaling. They interact with cellular quality control systems. And when their function deteriorates, the consequences can eventually appear on the outside of the body. That's why the mirror can sometimes show you the final chapter of a story that began much earlier inside the cell. And here's the part I find most exciting. In 2025, researchers published a study in the Journal of Investigative Dermatology showing that experimentally reducing mitochondrial function in the epidermis of mice accelerated features associated with skin aging, including impaired wound healing and hair regrowth. The researchers concluded that age-associated mitochondrial decline can actively contribute to skin aging rather than simply being a passive consequence of getting older. Now, a mouse study does not prove that repairing your mitochondria will erase your wrinkles, but it changes the question. Instead of asking, why does my skin get old? We can start asking, which parts of the aging process are actually modifiable? And mitochondrial biology may be one of those pieces. Maybe the future of anti-aging skincare won't be about finding one miraculous ingredient that sits on top of your skin and makes it look younger for a few hours. Maybe it will increasingly involve understanding what happens inside the cells themselves, how efficiently they produce energy, how well they remove damaged mitochondria, how they respond to UV exposure, how they control oxidative stress, how they communicate with fibroblasts, how they enter and escape cellular senescence, and how we can influence those systems without simply throwing more and more products at the surface. So no, I wouldn't tell you that you can currently fix your mitochondria and reverse your biological age. Science isn't there yet. But I would tell you something much more interesting. Your mitochondria are not just tiny batteries sitting inside your skin cells. They are part of a dynamic system that helps determine how your skin responds to damage, repairs itself, maintains its structure, and adapts to the environment. And that means the story of aging skin may not be as irreversible as we once imagined. The goal isn't to make your cells believe you're 20 again. The goal is to give them fewer reasons to behave like they're under constant attack, while supporting the systems that help them repair, recycle, and adapt. Because your skin is not simply counting birthdays, it's responding to everything that happens to it. And some of those signals are still within your control. That's all for today. Subscribe for videos which bring new perspectives to what you already know.